share my screen. Is the screen visible?
Yes, sir. It's in presentation mode.
Yeah. Kunal, is it visible?
Yes, sir, it's visible.
Sapan?
Yes, sir, I can see that.
Kaveri?
Yes, sir.
Okay, so let's begin. Today is lecture 13 and we want to do hypothesis testing with proper terminology and concepts. So we started these lectures about a year back, if you recall. And now we are entering hypothesis testing proper. That was the original aim. This is what we started our probability lecture series with. Why probability is useful in AI, and hypothesis testing happens to be a very important part of that enterprise. Now, this example was shown some time back. An example adapted from Sheldon probability, a very celebrated book on probability, adapted from the example given in that book to an NLP situation. So some of you would recall this example. A company has made a Hindi Konkani machine translation system. Okay, it is called Bhattacharyya. And that system has been tested on 9 test corpus. And the blue scores on these 9 test corpora are 5, 8.5, 12, 15, 7, 9, 7.5, 6.5, and 10.5. Okay, so this is a set of blue scores, that is performance figures based on 9 test corpora. Okay, and these blue scores are reasonable. Okay, they are near 10, and therefore there is some hope for this particular machine translation system called Bhattacharyya, doing translation between Hindi and Konkani. And suppose somehow we know that if this machine translation system could be tested on the whole population, okay, sample by sample, you take many samples, large number of samples, and then you compute the blue score. The standard, the variance that you will get is 4. Standard deviation would be 2. Okay, so this is the observation on the data in front of us. Okay, and this data or observation is of supreme importance. Okay? Everything is guided by the observation that we make. The only assumption here, which sounds artificial, unrealistic, is that how do you know the variance of the whole population? It is known to be 4. So modulo that particular artificiality, there are many things to convey in this particular example. Okay, so we have a set of 9 numbers, and these 9 numbers are our observation or data. Now, from these 9 blue scores, which are performance metrics, we get the sample mean as 81. This 5 plus 8.5, etc., sum to 81. And 9 members in the sample size is 9. So 81 by 9 is 9. So the sample mean is 9. Okay, and we know from the maximum likelihood estimate that the best possible estimate, given the constraints, given the data in front of us, is the sample mean. The best estimate for the population mean is the sample mean. You cannot do anything better. Okay, if you have no other information. And the standard deviation is known to be 2. Now, one more thing we know, we'll come to this derivation, remind ourselves of this derivation a little later.
I can't hear you, sir.
Oh, you can't hear me? What about others?
So we can hear.
We can hear you, sir.
So someone rejoin, I think. Okay. Okay. So for 95% confidence interval for mu, okay, the value is 9 minus 1.96 into 2 by 3, comma, 9 plus 1.96 into 2 by 3. So this is a result which is known based on theory of probability, that the 95% probability under the standard normal curve is contained within the interval minus 1.96 to plus 1.96. Okay, so 95% of the area lies in this interval, minus 1.96 to plus 1.96. Now, if the sample mean is given, then we know that the population mean has to be between 9 minus 1.96 into 2 by 3 to 9 plus 1.96 into 2 by 3, where 2 is standard deviation, 3 is square root of n. So if x bar is the sample mean, then the population mean will be contained within x bar minus 1.96 into sigma by root n to x bar plus 1.96 into sigma by root n. This is a result which is known from the theory of probability, z values, and so on. This is a very powerful result that if I have the population sample mean, then with 95% confidence, I can say that the population mean will be in this interval. Very powerful result. And 95% confidence means that the probability of the population mean lying in this range will be 95%. Okay. And this kind of reasoning is at the heart of test of hypothesis. Now, based on the observation, which is 9 samples, and the knowledge obtained somehow that the variance is 4, we reach the 95% confidence interval as 7.69 to 10.31. That means the population mean will lie between 7.69 and 10.31 with probability 95%, with probability 0.95, okay, within this range. What is the consequence of this? If the maker of this Bhashantar system, if the company says that I can assure you that the blue score of 15 will be obtained. Okay, you run my translation system, get Hindi to Konkani translation. I guarantee that you will get a blue score of 15. Now my 95% confidence interval gave me the range 7.69 to 10.31. How can I trust him? I cannot trust him, okay, if I have this particular interval in mind. So if this 95% is my confidence level that I want, or I want to make an error of only 5%, then I cannot trust this claim. On the other hand, if the maker says I can assure blue score of 10, we cannot reject his claim. Okay, and we can trust with 95% confidence. So all this is coming out of this simple observation of interval, confidence interval. Okay, given the sample mean, the population standard deviation, and the sample size, I can get an interval within which the population mean will lie, which is something you should really reflect on and wonder. Okay, I can give a bound within which the population mean will lie, based on the sample's observation, the size of the sample, and somehow the knowledge that standard deviation is sigma. Okay, so a claim of 15, I am inclined to reject. A claim of 10, blue score, I am inclined to accept. I cannot reject. Now we'll make this little more formal. Reject, accept, and so on. So we come to this very important notion of interval estimate. So if x1, x2, x3 up to xn is a sample from a normal distribution having unknown mean mu and known variance sigma square, then the maximum likelihood point estimator of mu is x bar, which is sigma xi by n. This is the maximum likelihood point estimator. Okay, and this is also one of the triumphs of probability theory, which says that sample mean is the best estimate of population mean. Now, another thing we know, if we take many samples and keep calculating the mean from the sample mean from the samples, then it is obvious that with the samples, the sample mean will also vary. Now the samples are being collected from a normal distribution. This sample mean is also normally distributed. Okay, and the mean of this mean distribution is mu, the population mean, and the standard deviation is sigma by root n. So please observe this result that as we change the samples, the sample means also change. So sample mean becomes a random variable because the samples are changing. The mean of that random variable is population mean. And the standard deviation is sigma by root n, which comes from what is called the central limit theorem. Okay, central limit, we took a long time, many lectures to describe central limit theorem, its application, and its derivation. We will, if necessary, revise those discussions later. So we know this powerful result that the sample mean is distributed with population mean as the mean and standard deviation sigma by root n. So if I subtract population mean mu from x bar, the sample mean, and divide it by sigma by root n, then you are subtracting mean and dividing it by dividing the difference by standard deviation. You get a standard normal distribution, which mean is 0 and standard deviation is 1. Okay, so this is fine. We have converted, or we have obtained a z variable, that is standard normal variable with mean 0 and standard deviation 1. What do? I subtract the population mean from the sample means and divide by sigma by root n. So then I know the following from the property of z. We know that z, probability of z lying between minus 1.96 to plus 1.96 is 0.95. So I do this algebra, probability of minus 1.96 less than x bar minus mu by sigma by root n less than 1.96. This probability is equal to 0.95. Now I do algebraic manipulation. I take sigma by root n to the left hand side of the inequality and to the right hand side of the inequality. There are two upper and lower intervals, minus 1.96 and plus 1.96. Then I get x bar minus mu lying within minus 1.96 sigma by root n and 1.96 sigma by root n. So from to conclude, mu, the population mean, is greater than x bar minus 1.96 sigma by root n and less than x bar plus 1.96 sigma by root n. That means population mean is lying within plus minus 1.96 sigma by root n of x bar. If I get the sample mean, then I am able to give an interval estimate for mu with confidence 0.95. The probability of the population mean lying within this range will have to be 0.95. So this is the derivation behind that observation that the blue score will lie between 7.69 to 10.31. Okay, so now we are going towards test of hypothesis, and we are introducing a very important concept called Z critical. Z is the standard normal variable, and we are introducing a notion called Z critical. I start with this question: can the blue score for Bhashantar be 10? So I do the following calculation: x bar sample mean minus 10 divided by sigma by root n. So x bar is 9, sample mean is 9. 9 minus 10 divided by 2 standard deviation, root n is root 9, which is 3. By doing these calculations, I come to the conclusion that this x bar minus 10 by sigma by root n is minus 1.5. This I'll call as Z observed. If you remember the discussions on chi-square, there were two quantities, observed and critical. So I call this quantity Z observed, minus 1.5. And Z critical is, on the negative side, Z critical is minus 1.96. And I observe that Z observed, which is minus 1.5, is greater than Z critical on the negative side, which is minus 1.96. I've just observed this. I'm not drawing any conclusion now. Take another question, which is, can the blue score be 15? I can deal with this situation. X bar minus 15 by sigma by root n. 9 minus 15 by 2 by 3. That gives me minus 9. Now, Z observed is minus 9. Z critical on the negative side is minus 1.96. Here Z observed is less than Z critical. Earlier value, Z observed minus 1.5 was greater than Z critical. So notice this, okay? Blue score being 10 gives me Z observed greater than Z critical on the negative side. And blue score of 15, which the company was claiming, gives me Z observed less than Z critical. Let us note this. Now, I have another claim. Blue score is 3. Suppose the competitor of the company comes and says that, "Nee, nee, unse mat kharidna. Don't buy Bhashantar. Buy from me." Because Bhashantar's blue score is 3. Okay, blue score is 3. What do I do with this value? I again compare with Z critical. If I take 3, then x bar minus 3 divided by sigma by root n. 9 minus 3 divided by 2 by 3, 6 divided by 2 by 3, 18 by 2, which is 9. Here I find that Z observed is 9, and the Z critical on the positive side is 1.96. So here Z observed is greater than Z critical. I am still drawing no conclusion. I am just making observations about these claim situations. Claim of 10, Z observed less than Z critical on the negative side. Claim of 15, Z observed is greater than Z critical, falling outside Z critical, that is. And minus 1.5 was falling within Z critical. So falling outside and falling within is important. And the adversaries or the competitors claim that Bhashantar's blue score is 3. I ask myself, can it be so low? Well, I see that Z observed in that case becomes 9. And Z critical is 1.96. Z observed is far, far bigger than 1.96. Again, falling outside Z critical. So this is taking us really towards test of hypothesis. We have introduced an important notion called Z critical. Okay, the yardstick against which I'll compare my Z observed. Now I come to the instrument that is available to me and a situation which is consistent with that particular instrument. Okay, so far the claims were for Z blue score equal to some value, 10, 3, 15, and so on. Since I have an interval minus 1.96 to 1.96, let me look at a claim which is also an interval kind. Okay, can the blue score be between 8 and 10 is something I ask. Okay, my original platform was interval. My question asked is also interval. I will call this question a hypothesis. Okay, I formulate the hypothesis. The blue score is between 8 and 10. All right, so in that interval, I take the lower boundary, which is 8. Now, x bar minus 8 is x bar minus 8 divided by sigma by root 10. 9 minus 8 is 1 divided by 2 by 3. And the calculation gives me 3 by 2, which is equal to 1.5. So in this case, the Z observed on the lower side of the interval is 1.5. Okay, so for the interval, Z observed on the lower side is 1.5. What is the upper limit of the interval for my hypothesis? 10. So x bar minus 10 is 9 minus 10 divided by 2 by 3, minus 1 by 2 by 3, minus 3 by 2. I get minus 1.5. Okay, so I get an interval of Z observed, which is between minus 1.5 and plus 1.5. So when I have this hypothesis, the blue score is within 8 to 10. I have a hypothesis, I have an observed, Z observed interval, which is between minus 1.5 and plus 1.5. And what is minus 1.5 and plus 1.5? Isn't it contained within minus 1.96 and plus 1.96? Yes, it is contained. That this interval is contained within the Z critical interval, which is minus 1.96 and plus 1.96. Since that Z observed interval is not falling outside the interval, critical interval, I cannot reject the hypothesis. Okay, why can't I reject? I'm coming to that very soon. You had seen this machinery in chi-square distribution also. We are doing this now for test of hypothesis for numbers. Okay, so we have come this far by introducing the notion of hypothesis and notion of Z critical. So can somebody verify that you are able to hear me and you are looking at the screen which says between 8 and 10?
Yes, sir.
Yes, sir.
Okay, okay. Okay, so far so good. Now, I have just examined whether an interval is consistent with the data. Now, in dealing with this, Sapan has asked a question. Sapan, can you repeat the question?
So when we say cannot reject, does it mean we accept?
Okay. Okay, just coming to this. Okay. Yeah. Good question. Yeah. So what is the hypothesis in this case? The blue score of Bhashantar lies within 8 and 10. This is the hypothesis. And we'll call this hypothesis the null hypothesis. Okay. I have slides for showing you the null hypothesis, definition of null hypothesis, and so on. So this is the hypothesis I have in front of me. The blue score of the Bhashantar lies within 8 and 10. So why cannot we reject this hypothesis? just because the Z observed interval is contained within my critical interval. Why, if it is between minus 1.96 to plus 1.96, the interval is a sub-interval of the critical interval. Why can't we reject the hypothesis? Okay, we proceed towards that. We give a pictorial depiction now of 5% confidence interval. So look at this standard normal curve, mean 0, standard deviation 1. Look at these plus 1.96 and minus 1.96. You take the area of the curve from plus 1.96 to plus infinity and minus 1.96 to minus infinity. Add these two areas. These two areas are 0.05. And leave out these two areas. The area from minus 1.96 to plus 1.96 is 0.95. Okay. So similarly, we get 68% interval, which is minus 1 to plus 1, and 99% interval, which is minus 2.58 to plus 2.58. So this curve is so important, and these intervals are so important. Whole of interval estimation, test of hypothesis are founded on just one curve, this curve, the standard normal curve, and the area under that curve, and intervals giving 95%, 99%, 68%, and such probability values. So for the Bhashantar problem, we see that x equal to 10.31 will give me z equal to minus 1.96. And x is equal to 7.69 will give me z equal to plus 1.96. Okay, so to be within this interval minus 1.96 to plus 1.96, the blue score has to be between 7.69 to 10.31. Notice that this 10.31 is now to the left and 7.69 is to the right. Okay, notice this point. Let us not make the mistake of placing 7.69 to the left of 0 and 10.31 to the right of 0. Okay, because this curve is for z value, not x value. Now, if I take z, the range 8 to 10, then x equal to 8 will make z equal to 1.5, some point here, and x equal to 10 will make z equal to minus 1.5, some point here. So minus 1.5 to 1.55 is indeed a subinterval of minus 1.6 and plus minus 1.96 and plus 1.96. So this is two-sided 95% confidence interval. Oh, okay. Now, a more practical situation is what is called one-sided interval, the upper interval and lower interval. Suppose I want 95% confidence. Then what is the Z critical if I consider only upper interval? That means only the region from Z critical to plus infinity. Okay. Obviously, since I'm not able to make use of the negative side probability, this 1.96 will shift leftwards, right? I have to cover 0.05 area, and I'm not able to get 0.025 from the negative side. So the Z critical now becomes 1.645. So the area from 1.64.5 to infinity is 0.05. So the area to the left of 1.645 is 95%. Similarly, if I'm not allowed to make use of the positive side, I'm not allowed to make use of the probability of 0.025 from the positive side, then my boundary has to shift from minus 1.96 towards 0. It becomes minus 1.645. So the area from minus 1.645 to infinity is 95%. the area from minus infinity to plus 1.645 is 95%. So these are called one-sided confidence intervals. Okay, one-sided confidence intervals. Where are they useful? They are useful when my hypothesis asks a question, is the value greater than a particular value or less than a particular value? Okay, in such cases, I have to do one-sided confidence interval. And two-sided confidence interval is used when the problem is asking a question in the form of an interval itself. Okay, with lower bound and upper bound specified. When the hypothesis is asking is something greater than another quantity or less than another quantity, then we have to use one-sided confidence interval. And let us very clearly remember this, that for symmetric interval, 95% area is between minus 1.96 to plus 1.96. For one-sided confidence intervals, minus infinity to plus 1.654 is 95% of the area, and minus 1.645 to plus infinity is the 95% area. They are to be used for one-sided interval estimate. So for one-sided test, what should be the X value? If somehow we know that the accuracy is at least equal to the sample mean, then the test of hypothesis will involve one-sided test. If we know the sample mean is no more than the sample, then to the test of hypothesis will be one-sided. So one-sided is more practical, more frequent than the hypothesis being asked with lower bound and upper bound given. Now we introduce the terminology for the test of hypothesis. These are the building blocks for test of hypothesis. First notion is that of null and alternative hypothesis. H0 is the notation for null hypothesis, the hypothesis we want to reject. So look at this red string, reject. So we take an adversarial position, an aggressive position. Okay, the null hypothesis is the one which has to be nullified. Okay, it is a hypothesis we want to reject. So that's how one forms H0 or null hypothesis. Okay, null hypothesis is never linked with accept. The fate of null hypothesis is it will face always face the situation of being rejected. Okay, its fate is this: the data would like to reject this hypothesis, and we will have to say whether based on the data we can reject the null hypothesis or not. Now Swapan was asking, if I don't reject, does it mean I accept? Okay, so now since we are in the world of probability, there is no black and white. Everything is gray. Okay, so there is no 0-1 decision. It is always with a probability. So when we say we cannot reject a hypothesis, this is always with a probability. So if we reject a hypothesis with probability P, then we are accepting the hypothesis with probability 1 minus P. Okay, so when we say cannot reject, there is something unsaid there. We cannot reject with some probability. Okay, so let's make it more clear as we go ahead. So remember how to form null hypothesis. Null hypothesis is a hypothesis which will eventually be rejected or not rejected. So this is an adversarial position. HA or H1 is the alternative hypothesis. This is the opposite of H0. And we use the sample statistics trying to reject H0. So let's now, with this terminology, let's go back to the question of whether the blue score can be within 8 and 10. Can the blue score be within 8 and 10? Okay, we had that hypothesis. So I'll form this null hypothesis. The blue score is between 8 and 10. So H0 is blue score is between 8 and 10. Now I will be looking out for rejecting this hypothesis. Okay, rejecting this hypothesis. What is the reason? Okay, the reason is here. The reason is introducing a new terminology called the p-value. Called the p-value. Introducing a new term. We had introduced interval estimate, confidence interval, significance interval alpha, that is 1 minus 0.95. We introduced Z critical. Now p-value, a new term. I'll just read it. This is a good description of p-value taken from Wikipedia. The p-value or the probability value tells you how likely it is that your data could have occurred under the null hypothesis. The p-value is a proportion. P-value of 0.05 means that 5% of the time you would see a test statistic at least as extreme as the one you found if the null hypothesis was true. Okay, so null hypothesis is something we want to reject. You cannot reject the data. The data is in front of you. The observation has been made. The 9 blue scores we have seen, you cannot reject them. So everything you do has to support the data. You cannot be inconsistent with the data. Okay, this is another pillar of test of hypothesis. And again, if you look at it carefully, this goes to the maximum likelihood estimate. Let me illustrate this with a very familiar example that we know. Let us take the coin toss situation. I have made 5 tosses. The tosses are head, tail, head, tail, HT, HHT, HT, HHT. How many heads here? The number of heads is 3 out of 5. What is the best estimate for probability of head? 0.6, 3 by 5. What is the best estimate for probability of tail? 1 minus 0.6, 0.4. Now, this is the parameter that has been estimated. Probability of head 0.6, probability of tail 0.4. Under this assumption, or under this parameter, what is the probability of the data? The probability of the data is probability of HT, HHT, which is 0.6 to the power 3 into 0.4 to the power 2, comes out to be 0.036. I'm sorry, this should be 0.036. Okay, so the probability of the observation is 0.036. The parameter values are 0.6 and 0.4. I'm telling you again the cardinal principle, something which you cannot trifle with, something which you cannot take lightly. The data has happened. The coins have been tossed and these observations have appeared. HT, HHT, they're sacrosanct. You cannot do anything. You cannot close your eyes to the data or the reality. Under that data observation, the best estimate for head is 0.6, best estimate for tail is 0.4 by maximum likelihood principle. Okay, so you set up the maximum you set up the likelihood expression for observation, maximize it by taking derivative with respect to probability of head, and that maximization gives you probability of head is 0.6 and probability of tail is 0.4. Can you now reject the hypothesis that probability of head is 0.6 and probability of tail is 0.4? Can you reject it? No. You cannot reject it because this is the observation which has happened. You cannot reject the data. and you cannot reject the maximum likelihood principle. Okay, so the data is here to stay. Probability of head 0.6 and probability of tail 0.4 is here to stay. The probability of the observation is 0.36. This is the p-value. Okay, this is the p-value, the probability of observation. The probability of head being 0.6 and the probability of tail being 0.4 gives me the p-value of 0.036. I'll make this correction. This is 0.036. Okay, so this is an analogy which I am using to help us understand the concept of p-value and the test of hypothesis. Okay, if the data is true, your probability value for head and tail cannot be anything other than 0.6 and 0.4 if maximum likelihood principle is true and the data is true. Okay. Similarly, the probability of the blue score being in interval 8 and 10 cannot be rejected. Okay, cannot be rejected if the data is true. So I cannot reject the probability of head being 0.6 if the data is true. So this is the notion of rejection acceptance. Okay, I cannot reject the probability value of head to be 0.6 if the data is in front of me. Okay, so this is the cornerstone of test of hypothesis. We'll stop here today and take this up. Remember this nice example of coin toss. Maximum likelihood principle is again at play here. Okay, just like maximum likelihood principle gave us a method of estimating the parameters of a distribution, again maximum likelihood estimate is giving us a method of testing of hypothesis with an additional machinery. That additional machinery is the standard normal curve and the probability under that curve. These two instruments, maximum likelihood and standard normal curve, is giving us a platform for discussing test of hypothesis. I'll stop here today. We started a bit late, but our next meeting will begin at 11. So we'll continue this discussion. Okay, and do please remember these terminology: interval, standard normal curve, Z critical, H0 null hypothesis, HA alternative hypothesis. And remember what H0 always faces. From the time it is born, H0 faces adversity. People are out to reject it and reject it in the face of the data. What is the reason? I cannot reject the data. So what can I reject? I can reject the hypothesis. So data being sacrosanct, can I reject the hypothesis or not? Okay, this is the point. So any question, point from anybody? Am I still audible?
Yes, sir.
Okay, so we'll stop now and come back in about 5 minutes for our work update meeting. Kaveri has sent a link. Okay, thank you.
Thank you, sir.
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 Thank you, sir.